We'll begin by learning how to evaluate trigonometric integrals involving powers of sine and cosine. These integrals look like this. The key idea is to use the following trigonometric identities to transform the integral into a form that's easier to integrate. The trigonometric identities that we're going to use are the Pythagorean identity, sine² plus cosine² is equal to 1. And then the second ones are the power-reducing identities for sin²x and cosine²x. Integrals involving powers of sine and cosine can be categorized into three cases. Case 1 is when the sine power is odd. Here's an example of this case. Notice that sin² is raised to the third power, which is odd. To make things easier, I've written down 3 steps that we can follow, and we'll go through these steps one by one as we walk through this example. We're going to integrate sin³ of x times cosine² of x dx. Step 1 is to pull off one sin² and group it with dx. Let's do that. If we pull off one sin², we're going to have a sin² left, so we have sin²x times cosine²x, and then the sin² that we pulled off, we're going to group with dx. The reason that we're doing this is because notice that this leaves us with an even power of sine, and we can convert that to cosine using this trigonometric identity that I put up here on the right. And then we have sin² dx, which is the derivative. Let's see how this works. Step 2 is, just like I said, we're going to use the identity sin²x is equal to 1 minus cosine²x to rewrite the remaining powers of sin² in terms of cosine²x. We'll write down step 2. And instead of sin²x, we're going to put in 1 minus cosine²x. And then we still have cosine²x, and then our sin² dx. Let's go ahead and multiply this through. This gives us cosine² minus cosine to the 4th x, all times sin² dx. Let's look back up to our steps and look at our third step. In this step, we are going to let u equal cosine²x, and we'll integrate using u-substitution. We have u is equal to cosine²x, and just like we talked about, our du is equal to minus sin² dx, and we have that right in our integrand. We'll have to watch out for the negative here. We have u² minus u to the 4th, and then we have a minus du. Let's go ahead and let's rewrite this and get rid of that negative. This gives us u to the 4th minus u² du. Now we just go ahead and let's integrate. This is u to the 5th over 5 minus u³ over 3 plus our arbitrary constant. Now all we have to do is plug back in, and u, let's see if we can find it up here. U is equal to cosine²x. So this gives us 1/5 cosine to the 5th x minus 1/3 cosine³ plus c. I like bringing those constants out. I just think it makes the answer nicer. And there's our final answer. Working through problems like this trains your brain to recognize patterns, choose an approach, and transform complicated expressions into simpler ones. By doing this, you're developing the mathematical flexibility that you're going to need for Calculus 2, and then courses like differential equations and all of those beyond that. Let's now look at case 2 of integrals involving powers of sine and cosine. Case 2 is when the cosine power is odd, such as the 3 in this example. I've written down the steps that we can follow, and we'll walk through these as we walk through our example. We're going to integrate cosine³ dx. Our first step, written right up here, is to pull off one cosine x and group it with dx. Let's go ahead and let's do that. This gives us the integral cosine²x. That's what's left when we pull off one cosine x. And then we're going to group our cosine x with our dx. The reason that we did this is we can now write our cosine²x in terms of sine squared, and then this cosine x dx is our derivative. Let's look at step 2. I kind of just went over this. We are going to rewrite cosine squared in terms of sine squared. So our cosine²x is 1 minus sine²x. I put that identity up on the right so that you'll have it. And then we have our cosine x dx. Now let's look at step 3. We are going to let u be equal to sine x, and we're going to integrate using u-substitution. We'll let u be sine x, and then we'll rewrite our integral. This gives us the integral 1 minus u squared, and then our du is cosine x dx. So we'll just multiply this by du. Now we can go ahead and integrate it. The integral of 1 is going to be u, and then we have minus u cubed over 3 plus our arbitrary constant. And then the last thing we have to do is to just look back up here and see what we put in for u. We put that u is sine x, so this gives us the answer sine x minus, I'm going to pull that 3 out in front, so minus 1/3 sine³ x plus c. And there's our answer. In case 3 of integrals involving powers of sine and cosine, we have even powers of sine and cosine. We'll walk through these 3 examples and notice that all the powers of sine and cosine are even. In these examples, we are going to use one or both of these power reducing identities, so I went ahead and put them here in our green box so that we'll have them. I've written down 2 steps that we're going to follow. We're first going to rewrite the even powers of sine x and or cosine x using these identities until no even powers remain. I'll show you exactly what that looks like. And then we just have to integrate. Let's look at our first example. This is a classic one. It is the integral of sin²x dx. Following our first step, we are going to rewrite sin²x in terms of cosine²x. I put that identity right over here on the right. Notice in this identity that there is a negative in front of the cosine²x. Let's go ahead and let's plug that in. This gives us the integral of 1 minus cosine²x all divided by 2 times dx. I'm going to rewrite this, and I'm going to bring that 1/2 out in front just to make it easier. So in our integrand, we have 1 minus cosine²x dx. Our second step is to just go ahead and go through the integration. This gives us 1/2 times x. Now let's see, the integral of cosine is positive sine. So the negative comes along for the ride, and we have a positive sin²x, and then we have to divide by 2 because of the 2 multiplying x, and then we add our plus c, and this simplifies to 1/2 x minus 1/4 sin²x plus c. And there's our answer. Let's now look at example 2. we are going to integrate cosine²x dx. To do this, we are going to need to use the identity over here on the right in our green box, cosine²x. It's written in terms of cosine²x, and notice that there is a plus in front of the cosine²x. The reason that we're using this identity is we don't know what the integral of cosine squared is, but we do know what the integral of cosine is. Let's go ahead and let's substitute this in. We have 1 plus cosine²x, all divided by 2 times dx. I am going to take the 1/2 out in front, and we have 1 plus cosine²x dx. Our second step is to just integrate this. Our 1/2 comes along for the ride. Integral of 1 is x. The integral of cosine²x is a plus sin²x, but don't forget we have to divide by 2 because we have a 2x instead of an x. And then we have our plus c. Let's rewrite this, and our answer is 1/2 x plus 1/4 sin²x plus c. And there's our final answer. Let's now look at our third example. We're going to integrate sin²x times cosine²x. The first thing that we're going to do is we're going to look over here on the right at our formulas, and we're going to use the power reducing identities, sin²x and cosine²x. Let's go ahead and let's put these in. This gives us the integral of 1 minus cosine²x, all divided by 2, times 1 plus cosine²x, all divided by 2, and then we have our dx. Let's pull the 1/4 out in front, and then let's go ahead and let's multiply these two quantities right here. I'll highlight them. This one and this one, we're going to multiply these out. This gives us a 1, and then notice the middle terms cancel out. That's really nice. And then we have a minus cosine² 2x dx. Now, what we have to do is keep using these power-reducing identities until we have no squared term left. So we'll use the power-reducing identity for this term. And let's go ahead and let's write that out before we use it because the angle is a little bit different. So let's say that cosine² 2x, looking right here, that is going to be equal to 1 plus cosine. We're going to double the angle, so 2x becomes a 4x, and then we divide by 2. Let's put this in and see what we get. We have 1/4, the integral, and now we have 1 minus 1/2, I'm just distributing that through, minus 1/2 cosine 4x dx. It's really helpful to go ahead and simplify as much as you can before you integrate. This gives us 1/4, and then we have 1 minus 1/2, so this is 1/2 minus 1/2 cosine 4x dx. Let's go ahead and let's pull the 1/2 out. So the 1/2 and the 1/4 make a 1/8. We have the integral 1 minus cosine 4x dx. Now we can integrate. That's our step 2. We just integrate this. So this gives us 1/8. The integral of 1 is x. The integral of cosine is positive sine, so the negative comes along for the ride, and this becomes sine 4x. Don't forget we have to divide by 4 because of that angle, and then we have our plus c, and we can rewrite this nicely as 1/8 x minus 1/32 sine 4x plus our arbitrary constant c. And there's our final answer. The key to these problems is to keep using the identity until there is no squared term left in the integral.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.